A friend of mine had this problem. She wanted to show that any number of the form 2 to the power 2n minus 1 is divisible by 3, or you could say, is equal to 3 times some integer k. Now, she had some kind of formal, mathematical, proofy way of doing this, but I didn't really follow along. We can at least start by looking at some examples to see what we're dealing with. If we plug in n equals 1, then 2 to the power 2 equals 4, minus 1 is 3, that's fine. If we plug in 2, then 2 to the power 4 equals 16, minus 1 is 15, that's also good. For n equals 3, we get 63, and for n equals 4, we get 255. Long story short, it seems to hold up. Now, just glancing at these numbers, I don't see any immediately obvious pattern. The number k does show a pattern, in that it's always the previous k plus the next even power of 2, but that's more of an observation than an explanation. It doesn't immediately reveal why it works, we just know that it does. But you know, whenever I see 2 to the power of something, I immediately start thinking of binary. So let's ignore the k for a moment and take a look at these numbers in binary. 3 is 1, 1. 15 is 1, 1, 1, 1. 63, 1, 1, 1, 1, 1, 1. And I think you see where this is going. Not only do the numbers consist entirely of 1s, but there's always an even amount of them. Like these little pairs of 1s are the building blocks that these numbers are made of. And of course, a pair of 1s is just the number 3. What's happening here is that by multiplying n by 2, we make the exponent always even, and so the binary string is always of odd length. Then, when we subtract 1, we get a string that we know is of even length, and consists entirely of 1s. If we cut this string into pieces, we can see that it's really just a bunch of 3s that have each been pushed to the left by a different amount. You know how in base 10 you can push something to the left by multiplying it by 10? Well, in base 2 it's the same thing. You can push something to the left by multiplying it by 2. In a programming context, this would be called a bit shift. Each of these building blocks is just a 3 multiplied by a 2 to some power. And then we just add them up. 63, for example, is just 3 plus 12, which is 3 times 4, plus 48, which is 3 times 16. So then it's obvious that we can factor a 3 out from every term and let the rest be k. If we look back at the pattern we saw in k earlier, it makes perfect sense now. What we're doing is we're taking the previous number in the series, and then basically tacking on another 3 on the left, by multiplying it by the next even power of 2. Now that we know how this works, it's incredibly easy to form our own. This 2 refers to the base, which in this case was binary. This 2 refers to the length of the building block. The minus 1 means that the building block will always consist of the largest digit that the base supports, which in binary was 1. And the 3 is just the value of the building block after you know everything else. So we can do a weird one. Let's use a base of 5 and a building block length of 3. I know the building block will be made of 3 4s, since 4 is the largest digit in base 5. So if the building block is 444, then its value in decimal is 124. So, I can say that 5 to the power 3n minus 1 is divisible by 124. Try a few values of n and see that it works. Convert them to base 5 and see that they match the pattern we were expecting. You can try playing around with this, adding more terms, maybe making more use of n somewhere. Perhaps you can make the building blocks more interesting, instead of just the largest number possible, some kind of repeating triplet or something like that. I'll let you figure that out. I think this is a nice reminder of the relationship between exponents and different number bases, and the fact that binary has uses outside of computer science. Thanks.